Hello BC Calculus students, this is Mr. Johnson and this is the fourth video for section 8.4 and we're going to finish the examples. So we're going to work on example 17 through 22 and there is some new material here. However, the convergence tests are done. You've done all 10 convergence tests. So the first example is on the radius of convergence. So let me kind of loop back to some of the concepts we were just talking about with regard to the center and the interval of convergence. So for example, if you have a situation where you have a center of A, let's say, so that's our center, your series is going to look like this, where you have some situation where A sub n is your generator of sorts, where you have maybe n factorial, you have alternators in there, you have something to the power of n or whatever that case may be, but then you also have x minus a to the power of n, and x minus a is going to notate what the center is. So the center would be a in terms of how the series is set up or aligned. Now, if you find out that your radius goes from here to here, so let's say that this is our radius, and again, the radius is going to always be a positive value. So we have obviously the other side here, which is going to have a radius of the exact same length. The radius does not dictate to us how the interval works. So let's just hypothetically say that we have, I'll just put B here and C there. So let's say the interval is B is less than or equal to X is less than C, for example. The radius is between A and C or B and A, and the radius does not show whether or not the ends of the interval are convergent or if they're divergent. So in this case, you can see that by our interval, C is divergent and B is convergent. The radius doesn't have any impact on that. The radius literally notates the space between the center and the outer edge of the interval, not showing divergence or convergence at the outer edge of the interval. So the radius is simply just the distance from the center to the outside edge of the interval of convergence. So when we're being asked about the radius convergence, that's what we're being asked to find. Now, the ratio test, when you take the limit as n goes to infinity of a sub n plus 1 divided by a sub n, and you're looking for convergence, you know that that limit ratio must be less than 1. When you simplify this down algebraically, you're going to get a situation where you have the absolute value of x minus a, and it's going to be less than or equal to the radius. So where is the radius found? The radius is found by taking the ratio test, simplifying down as completely as you need to get x minus a. The absolute value of x minus a is less than whatever that value is then is the radius. Now keep in mind that if you, for example, got, let's say the absolute value of x minus 1 divided by 2 is less than 1. This is not in the correct form. You must move 2 so that it is x minus the center, and therefore in this random example I just came up with, the radius is 2, the center is 1. Okay, so let's try example 17. Now example 17, notice that the center is 4, and what we're going to do is take the ratio test of this particular problem to find the radius. So we have the limit as n goes to infinity of the absolute value, and it's important to keep the absolute value because we have this x that we don't know what it is. So we don't know necessarily if the terms are positive or negative. And we have, now keep in mind that we have x minus 4 to the power of 2n, and we're substituting n plus 1 there. It's a little different than what we've been working with in the other ones. So I'll just slow down in the algebraic simplification part of this one. So I'm going to write this as x minus 4 squared times x minus 4 to the 2n. And that comes from, if I take the 2 times the quantity n plus 1, if I distribute the 2, I get 2n plus 2, and I'm going to split that up so that I can simplify that in a moment. And then I have 3n times 3 to the first. And then, of course, 3n and x minus 4 to the 2n. None of that can really simplify. Okay, now again, this must be less than 1 if in fact the series is going to converge. So what we're going to do is cancel some items. So we have a cancellation here and a cancellation here. And we're left with the limit as n goes to infinity of the absolute value of the quantity x minus 4 to the second power divided by 3 is less than 1. In fact, I don't need that limit anymore because all of my n's canceled. So I'm going to just completely take out that limit because, again, we were able to cancel every term with n in it. We don't even have to worry about the limit anymore. I'm going to go ahead and take the absolute value of x minus 4 squared, and I've moved the 3 over by multiplication, and then I'm going to get rid of the square. So I have the absolute value of x minus 4, and it's less than the square root 3. And we are finally into the form that we want. Remember, the form is absolute value of x minus a is less than r. So guess what? The radius is square root 3, which is option C. All right, let's move on to the next page. Okay, example 18. So we're looking at the radius of convergence. So we take the limit as n goes to infinity of the absolute value of, I'm going to try to algebraically simplify this right away. So x minus 5 to the n times x minus 5. Again, I'm adding n plus 1 in for all my n's. 2n times 2 to the first times, this is kind of ugly, so it's 2 times the quantity n plus 1 plus 3 squared. So all of that is going to be a sub n plus 1. I multiply by the reciprocal of the original, which looks like this. Okay, if it converges, it is less than 1. So that's our beginning statement. Now we're going to want to cancel some items. So we can cancel x minus 5 to the n. We can cancel 2 to the n. We can also cancel the 2n plus 3 squared and the 2 times the quantity n plus 1 plus 3 squared, because remember, it's going to be a second degree polynomial divided by a second degree polynomial, same leading coefficients, and so we're able to cancel that because the limit is going to infinity. And what we're left with after applying the limit operator to this is the absolute value of x minus 5 divided by 2 is less than 1. And remember, we need it into the form, the absolute value of x minus a is less than r, and so therefore our radius is 2. All right, let's move on to example number 19. This one says that we have a series, says if the series a sub n converges, and a sub n is positive for all n, which of the following must be true? So again, must be true is what we have to look at. It can't just maybe be true. It has to be true. So first off, is the limit as n goes to infinity of a sub n plus 1 divided by a sub n equal to 0. So remember this portion right here, that's the ratio test. Now remember, the ratio test, if the series converges, is less than 1. So is 0 less than 1? Yes. However, the problem with this one is that could the limit be not equal to 0? Could the limit be something else? And the answer is absolutely. It does not need to be 0. It does need to be less than 1, but it doesn't need to be 0. So a is gone. It's almost too specific. The absolute value of n is less than 1 for all n. Well, think about series that we've had in the past. Maybe the first term is, I don't know, something that is larger than 1. I mean, it's certainly possible that you have a convergent series, and yet the first term might be something less than 1. I'm just thinking to myself about geometric series, for example, where you might have the first term as 2 or something like that. That's certainly possible. For C, does the series add up to 0? Well, probably not. I suppose it could, but that means that every term would have to be 0, which it says it can't be. So that doesn't make any sense. D and E are what we're left with. So think about with B, and maybe I'll try to show this. So if we look at, let me start with this. So if we're looking at the original, okay, we know the original converges. That means that we know that this is true, and it's true by the ratio test. That's just a fact. We know that that's true by the ratio test because it says that the series converges. So with letter D and letter E, let's say we take the limit as n goes to infinity of letter D. So we're going to look at, and we're performing the ratio test, by the way. So we're going to look at n plus 1 and a sub n plus 1. So I'm substituting n plus 1 in for the original, and I'm dividing by n times a sub n. Okay, and the question is this going to be less than 1 as n goes to infinity? And when we look at the relationship of n plus 1 over n as n goes to infinity, we get 1. And so this particular limit as n goes to infinity would simplify to the relationship that we end up getting with the ratio test, which is true. And in this case, we would have a convergent series. Now, the statement says in letter D that would somehow cause it to diverge. That's false. It's not going to cause it to diverge. It's actually going to have the same relationship that the original had. It's going to simply converge. However, if we take a look at letter E, so we have the limit as n goes to infinity, and I'm just going to substitute in n plus 1. So we have a to the n plus 1 divided by n plus 1 divided by a to the n divided by n. Okay, let's just simplify this down. So we have the limit as n goes to infinity of n a to the n plus 1 divided by n plus 1 times a to the n, or a base n. This particular one, and let me go ahead and change this to absolute values because we shouldn't have gotten rid of those. We don't really know what happens with the signs of n, for example. Okay, again, the question is, does this hold true for less than 1? And it does, in fact, because the limit as n goes to infinity of n over n plus 1 is simply just 1, and we end up getting the exact same relationship that we did in the beginning. The red equation that I have, or the red relationship I have by the ratio test above, we hold that relationship holds true. So in other words, when we're analyzing option D and option E, neither one of them changed the ratio test. And so therefore, when we're looking for whether or not the above statement a sub n converges for all a sub n greater than 0 for all n, which of the following is true, it must be option E, because as we divide by n, we're not going to change the particular convergence of the original series. All right, let's take a look at the next page in example 20. All right, example 20 asks for which of the following series converge. Well, the very first one is 1 and then -1 and then 1 and then -1 and so on. That's divergent. We're never really going to settle on any particular value. The limit does not exist there. And so whenever the limit does not exist, as n goes to infinity, maybe you could write it like this if you wanted to. We'll just call it a sub n. Does not exist. Then we have a divergent series by the nth term test. For the second one, what I would look at is the comparison test, because you have 1 over 2n minus 1, and you could compare it to 1 over 2n. The one on the left is larger because you're dividing by less there, and the series from 1 to infinity of 1 over 2n is divergent by the p-series. It's also harmonic. And so therefore we could say that the series 1 over 2n minus 1 is also divergent by the comparison test. All right, so we've struck out twice. 1 is gone and 2 is gone. For number 3, I would just rewrite this as, let's see, 1 divided by 3 to the n times 3 to the negative first. That's the same thing as 3 divided by 3 to the n. And that's the same thing, if you want to write it one more time, I suppose, as 3 times 1/3 to the n. And in this case, we have r equal to 1/3, and the absolute value of it is less than 1. So it's convergent by the geometric series test. So option 3 is our answer, and that is option C in the multiple choice. All right, let's move on to example 21. So with example 21, we're looking at the values of p for which both will converge. So if we take a look at the first one, this is a p-series test. And remember, the p-series test basically says that if you have 1 over n to the p, I know this one's 2p, so if the power, which is 2p in this example, is less than or equal to 1, then we have a divergent series. And if that power is greater than 1, we have a convergent series. So in this case, we're looking for p is greater than 1/2. That's what we're focused on for the first one in order to make it converge. For the second one, we're looking at a geometric series. So we're focused on, I'll just write down geo series. So we're and the first one, sorry, I should have written this down. This is the p series. All right, so for our geometric series, we're looking at the absolute value of p divided by 2 being less than 1 in order to make it converge. That's our focus. And if we take the absolute value of p, we multiply by 2, and then we set up our interval here, we get -2 to 2, and not including either one because of the geometric series definition. So we're looking for basically an overlap of the p greater than 1/2 and the p in between -2 and 2. And so what we settle on here is option C, which is that p is greater than 1/2 but less than 2 only. All right, let's move on to the next page and our last example. Okay, our last example here is example 22, and it says we want to consider the series -1 to n of a sub n, where a sub n is greater than 0. Which of the following conditions guarantees that the series converges? And a sub n is positive, so we don't need any absolute value here. And our answer is B, by the ratio test. It's kind of a nice way to end this section. That is the definition of the ratio test, and that is the definition that guarantees absolute convergence and therefore convergence. All right, that does it for section 8.4. Now there's some plenty of practice that follows, but in terms of the notes, that is it. Thank you.